Hello dear students. Today's topic of discussion is digital to analog converter. Digital to analog converter, there are different types are there. So we are mainly focusing on R-2R ladder type. So let's start with it. So here is the basic circuit diagram of R-2R ladder circuit. You can clearly understand why the name is R-2R ladder, because here we are having two type of resistance. One is this 2R, another one is R. All R we are using 2R and R. And at last, when we find out the output equation, there you will find out that RF is also replaced by R. Okay, so this is the basic diagram. So we all know about that. Digital to analog converter means I will be giving some input, digital input, suppose 1 1 0 1, and correspondingly what is that analog voltage that I am going to get in the output side. Here I have used one op amp. This is summing amplifier. As you can see here, we can give the different inputs this side, and all these input are going to the inverting terminal. So this is basically one inverting summing amplifier is used here. And if you can recall that output voltage equation will be V0 equal to V in multiply with RF by R, or I can say R1. Now here, because it is an inverting amplifier, so here one minus will come. Okay, so minus V in RF by R1. It is the value of the output voltage in case of summing amplifier. So here, as we can see, because we have to convert the digital signal to the analog version, digital signal like 1101, this 1101 we have to give in the input side of this R2R ladder. Okay. We are having this kind of structure, as we can see, this R2R1. So here we have to give this input. One more thing is there, when we are giving this input, we have to keep in mind that if the input is 1, then if the input signal, if the input digit is 1, then V reference will go as input. When input digit is 0, then it will be connected to ground, means you can say 0 will be going over there. You can clearly see the diagram of how the circuit is connected. This B0, B1, B2, B3, these are the bits. These are the bits which we are going to apply over here to the input terminal. And to assign that whether the input digit is 0 or 1, what is the input digit, accordingly, see here we are having a switch. The switch will be switching from this terminal to this terminal. If it is 1, then it will be connected to this V reference terminal. If it is 0, then it will be connected to this ground terminal. See, this is the ground one, common ground terminal, and here one common reference voltage is given. So I think this much is clear to you all. So here we are applying the digits, the digital data which we want to convert to analog, and depending on the 10 value, the switch will be operate to the V reference and to the ground point. Next, see what we have to do. We have to find out the equivalent output voltage when we are applying this all these voltages, all these signals. Then what will the outcome? We know the summing amplifier, mainly the output is V out is equal to V1 plus V2 plus V3, like this. Means whatever input voltage we are giving to the input terminal, output will be the summation of all these voltages. So here we have to find out that if we are giving this 1 1 0 1, these different values, then what will be the output voltage. Let us consider in the upcoming slide what I have shown, that I have considered a 3-bit DAC. 3-bit DAC is considered. Okay, and for the 3-bit DAC you will be getting 3 stages. if you look very closely, if I use 3-bit DAC, means I'll be giving input to this terminal and this terminal. Okay, so the last resistance value is 2R. So in that case, when I am using, suppose this part is will not be there, so when I am using 3-bit, so this 2R structure will be there, then this R2R, like this it will continue for the 3 stages that I have shown here, the first stage, second stage and third stage. Okay, so we have to, this is the equivalent circuit you can say, and we have to find out the values. Next, see, because I have taken 3 bits, so first I have considered that B0 point, the B0 is value is 1 and B1, B2 is 0. Okay, if B0 and B0 position, you just have a look, the B0 position, here I have applied the B0, okay, the leftmost. So as B0 value is 1, it means how much will be the input to their stage, first stage, it will be V reference, because this thing already I have shown to you that here if in one value is given, input will be V reference. Okay. Next, see. So this is the first stage, second stage, third stage. Okay. We have to replace each of these stages, and finally we have to get that what is the equivalent Thevenin circuit for the given combination. Means like here we have given B0 equal to 1, B1, B2 is 0. Now for this pattern of 3-bit, what will be the final output V out, that we have to find out. So here we have applied Thevenin because we are finding out this VTH and RTH. So you can see when we applied Thevenin, so this resistance and this resistance, combining these two, the equivalent resistance, they are in parallel, as you can see, the equivalent resistance will be R. Okay, and here I have applied this V reference, it means it is applied across these two resistance. So the main Thevenin resistance will be VRF by 2, because these two resistance are having same value. This 2R, they are having same value. So the Thevenin voltage will be V reference by 2. So next stage, now see, this first stage is replaced. First stage is replaced by what? Replaced by this voltage value V reference by 2 and the Thevenin resistance R. So these two R2R, they are replaced by this R, and this V reference was given here because our B0 was 1. So here the voltage is now V reference by 2. Okay. Now here it comes the second stage. Again we have to solve the second stage. Here same situation is coming. Resistance R and R, they are in series. So altogether you can say here the resistance value is 2R. And the same situation 2R, this 2R, this the combination of these two resistance R and R, they are in series. So 2R and this 2R in parallel condition, and applied voltage is V reference by 2. So in the next stage, see, in the next stage, that's why the V reference is the VTH is given by V reference by 4, because here V reference by 2, here actually circuit, if I redraw again, so your circuit is like this. This part is as it is, R2R, this part is as it is, they are grounded. Okay, fine. So this is 2R, and these two resistance, these two, combining these two resistance, you are getting here 2R. Okay, and the voltage, applied voltage is, okay, the applied voltage is V reference by 2. So these 2R are in parallel. So combining these 2R, you will be getting the equivalent resistance R, and this V reference by 2 voltage is applied across both this 2R and 2R. So it will be also divided by 2, like the earlier case when you had V reference. That time the VTH value was V reference by 2. Why? Because this V reference was applied across both these 2R and 2R. They are same. So same way the voltage will be divided. So same way here also this V reference by 2 will be divided. That's why here again your RTH is R because of the combination of both 2R and 2R. You got this RTH value R, and your V reference, your VTH is V reference by 4. Earlier stage the value was V reference by 2, because V reference by 2 is divided among two of the resistance. That's why it is divided by 2. So its value is V reference by 4. Okay, up to this much is done. Then the next stage you can see here. So this is the third stage we are solving. So the third stage, what we can see, that VTH, this time what will happen, again this resistance are in series. So combining these two resistors, again we will be getting here 2R, and this 2R is also present. Okay, and the applied voltage, okay, this point is grounded. So this applied voltage is V reference by 4. So again this V reference by 4 voltage is divided to these two equal resistors. That's why the VTH value is V reference by 8, and these two resistors 2R, they are connected in parallel. So the equivalent resistance is R. So finally we got this final equivalent circuit, Thevenin equivalent circuit. Okay, so from here we can see that VTH I got this one, RTH is this. So this is the input right now. This is the input to your op-amp. We have considered a op-amp. Okay, summing amplifier we considered, right? So here it was RF, and here it was minus plus. So this circuit, this portion is connected to here. This portion is simply connected to here. Okay. Now this is simple inverting amplifier, because we have solved the circuitry. Here in the input side, whatever circuit we had, that we have solved, and we got the equivalent circuit as R input, and this V ref by 8 as an input voltage. So from here we can find out the output of simple inverting amplifier, which is given by V out equal to generally V in minus V in by RF by R. Okay. So here, because the input is VTH, or you can say V reference by 8, so that's why the voltage value is this, and I told you earlier the RF will be replaced by R. That's why here it is R by R. So finally it is like minus V reference by 8. Okay, this is the V out we got. This V out we got for the combination of, have a look, for this combination B0 equal to 1 and B1 B2 0. Okay, B0, this combination, this one we got for B0 equal to 1 and B1 0 B2 0. Now two more cases also we have to check out. The next one is same, B1 equal to 1, earlier B0 was 1, now B1 equal to 1, and B0 and B2 equal to 0. So same here you can check the equivalent circuit. Here the equivalent circuit 2R is there. Okay, then in between we are having R2R, R2R. Now what is the situation? My B0 is 0, B1 is 1 and B2 is 0. See, because B1 is 1, that's why the V reference is applied to this input terminal. Now switch will be shifting in that way that all these two terminals B0 and B2 will be grounded, and this B1 terminal will be connected to the V reference. Again we will be doing the same thing. So these 2R, they will be combined and you will be getting the RTH value to be R. Okay, as here these two are grounded, so there is, you won't be getting any kind of VTH over here, that will be ground only, simple ground. Next, this section you can see this previous stage R equivalent resistance R is here, and this is this R, and this 2R is as it is. Now here V reference is applied. Now combining this R and this R, now the situation is here the total resistance is 2R. So 2R again in parallel, so the equivalent resistance will be R. Okay, and this V reference is applied in this terminal is grounded, so I can say that the V reference is applied over here. Between this terminal and this terminal. So definitely this V reference is going to divide among this resistance and this resistance. So it will be basically getting half. That's why V reference by 2. And this resistance is what? This 2R in parallel. So the equivalent R is here. And this R and 2R is of the third stage. Okay. So let's see the final one. So here finally what we are going to get is again considering the op-amp inverting op-amp and RF value to be 1, RF as 1. So this one is grounded. Here we are applying this input. Here we have applied this input V reference by 4 via the resistance R. So actually it is connected like this. So in this case the V out is given by this minus V reference by 4. Okay. Now next case is B2 will be 1 and B0, B1 will be 0. Okay. So B0 is 0, B1 is 0 and B2 equal to 1. So here you can see as these two digits are 0, that's why these two terminals are now grounded, and B2 is 1, that's why it is connected to the V reference voltage. Again the same procedure we have to apply. We will be finding the equivalent resistance and voltage. See here there is no voltage, so means because it is grounded, so we have to consider the resistance only. So 2R in parallel, so equivalent resistance will be R. Now this R and this R, these two are in series, so the equivalent resistance is 2R. 2R and 2R again in parallel condition like the situation before, that's why the equivalent resistance will be R. This section equivalent resistance is this R, and this R is here and this 2R is here, and here the V reference is given. So it's clearly understood this V reference is applied here and it will be get distributed among these two resistance. Okay, this R and R will combine and it will form 2R. So this V reference is given to this both the resistance of same value, so the V reference will be get divided by 2. V reference by 2, basically it will be half, and these 2R and 2R in parallel, so the equivalent resistance will be R. So again this thing is going as the input of your inverting terminal of op-amp. Okay. So this is your R, RF actually, so it is given as the value R, and this terminal is grounded. This is inverting amplifier. Here we will be getting the output. So this V out will be equal to minus V reference by 2. Okay, minus V reference by 2. Now the total voltage when we apply all 3 digits, when we will be going to apply all 3 digits with suppose 111, then what will be the output? That generalized equation we have to find out. For that what we have done, see V out equal to what we are getting minus V0 V reference by 8. See when we consider V0 equal to 1, when V0 was equal to 1, that time we got the voltage, output voltage V reference by 8. When V1 was 1, we got V reference by 4. When V2 was 1, we got V reference by 2. Okay. Now we are considering that if all the values we are getting together, all the 1 we are getting, then what will be the generalized equation? So here this B0, B1, B2, they are simply the values. These are simply the values. Okay. Now if we are having 1, then this term will exist. Okay. If your B0 value is 0, then this B0 value is 0 means 0 into this term will be nullified. Okay. Now depending on the digit what you are giving, suppose 101, 110, 011, whatever combination you are giving, depending on that term will be nullified. Means if you are having any 0 term, any 0 digit is there, then that particular term will be nullified and rest of the terms will be added. Okay. So as we can see here, what we can write from this point, we can take out this V reference outside. So V out equal to minus V reference, same B0 into 1 by 8, B1 into 1 by 4 and B2 into 1 by 2. So we can write it further way that 8 represents what? 2 cube, 4 here it is 2 squared and 2 is 2 to the power 1. Okay. So for 3 digit, this is the generalized one for 3 digit. Now if we are having 4 digit, what will be the equation? For 4 digit, definitely the equation going to be minus V reference. Okay. So B0. Now 4 term will be there. Here see 3 digit, that's why B2, B1, B0. Now we'll start with B0 and it will go up to B0, B1, B2 plus 1 B3 term will come. Okay. So here how we going to do? See, with B0 what we are getting? With B0 we are getting the number of terms. Here 2, what is the power of 2? It is 3. And how many number of digit we are having? 3. So here if I am having suppose 4 digit, we are having, you can consider next year also you can see, we can consider the number of bit is 4. So here the power of 2 will be 4 plus B1 1 by next what will be the power? See here it was 3, then it is 2, it was 1. So it is gradually decreasing. So here the power will be 2 to the power 3, then plus B2 1 divided by 2 to the power 2 and finally last term B1 1 divided by 2 to the power 1. That's all. Okay. So for 4 digit means here we are considering one parameter, that is n, that is the number of digit. So here you can see the output voltage expression V out equal to minus V reference B0 multiply with 1 by 2 to the power n. 2 to the power n means the n is what? The number of digit. How many number of digit you are giving as input. And then gradually this 2 power is decreasing, n minus 1, n minus 2, like this it will continue up to 2 to the power 1. Up to 2 to the power 1 it will continue. Okay. I think it's clear to you all. If you have any doubts then you can comment, and if you like this then kindly like the video, and whatever topic you want to know from my side, please do let me know. Thank you all.